Thank you very much. It's, of course, a wonderful pleasure. Do I need a microphone? Do I need... I just speak here? Is it okay? So I'm very excited to be here. I had asked whether I was supposed to speak in English or Italian, and I was told I could speak in any language I like, even Italian, so it will be English. So I thought I would begin by introducing myself, where I come from, and then say something about the work I do. As you already heard, it's mathematics, so not familiar to everybody. I'll try to be gentle. So I am a mixture. I'm half German, half American. This started with my birth 73 years ago. I was born in both countries. I was born in Germany, but it was during the American occupation of American parents on American soil. So I have 2 birth certificates. And then my entire life has been mixed between the 2 countries. I got my undergraduate degrees in MIT, in America. My PhD I wrote in Germany. And that continued until a few years ago. I actually changed citizenship, and I now am no longer American, but I'm German. So I'm really a mixture. But actually, my life was much more international even than that. I've lived in 8 different countries, and for a period of almost 50 years, I had 4 consecutive 12-year periods. It was an accident, always 12, where I spent half of my life working in Germany and half as a professor in some other country. First 12 years in the United States, then 12 years in Holland, then 12 years in Paris, and now almost 11 years so far in Trieste, where I hope it will be at least 12. So that's for me. My family is also completely international. My father was born Polish, but later became British, then Swiss, then American. My mother, and he was a professor and a writer. My mother, who was a psychiatrist, was born Belgian, Flemish, not French, Belgian. We heard about Lemaitre, but she was Flemish. She was a psychiatrist, born Belgian, also became later American and later Swiss. My sister, who is also a psychiatrist, was originally American, but has lived for many years in London, is now also English. My wife, who is sitting here, studies the history of Japanese and Chinese mathematics in the 16th and 17th centuries. She's German, but was born in Poland. Our son is also German, but lives in America. So a complete mixture geographically. In mathematics too, and that's the reason for the title, I'm something of a wanderer. I started in topology many years ago because at that time people said that's the only interesting mathematics there is. All of the big discoveries in number theory and analysis had been made. Only topology is interesting. That was completely wrong, but that's what everybody believed. Then I did move to number theory, but in later years I've worked in many, many different fields of mathematics, and recently also, usually in collaboration with physicists, of mathematical physics. But there's one theme which has been common to practically everything I did. I'll come to it in a second, especially if I can understand this device. This is the theory of modular forms. Let me try this. No? Plus? No? How do I do? How do I click? I'm used to a blackboard. I'm a mathematician. I don't know how to use this thing. Okay. Ah, now it works. No, now it seems to be working. It was switched off. So if things are switched off, they can't work. So since most people don't know the word modular forms, I have to use it, but I won't try to explain what they are. It's a very beautiful class of functions, which was first studied in the late 19th century and early 20th century. And these are functions that have an infinite degree of symmetry. So if you think of a sine curve that you have all seen in your life, that has a degree of symmetry. You can move it by 1 unit to the left or right, and you repeat the curve. So it's an infinite group of symmetry, but a very simple one, just translation. Modular forms are something much more subtle. And they're absolutely beautiful, and essentially everything I've done has something to do with modular forms, somehow, sometimes rather hidden. So for today, I've chosen 3 topics, each of which involves modular forms, but all in very different areas. So let's see if this works. So the first area of applications are applications in number theory, which is the most natural. It's my main field. And here I had a choice, but I want to go back to the work that was mentioned by Professor Mattiucci with Benedict Gross on Hegler points from the 1980s. This is part of a famous and very beautiful theory from also the late 19th and early 20th century originally, but still very active, called complex multiplication. We proved an incredible formula. The formula is well over a page long. The proof is 100 pages long, but it's a formula. But this formula turned out to have many, many consequences, and so I wanted to indicate 3 of them. So for number theory, I'll give you 3 more specific things. So the first is, in a sense, very concrete. There are certain numbers called very explicit numbers, you can compute them on the computer, called singular moduli. And these are integers, j of 1, j of 2, j of 3, which I, of course, can't explain at all where they come from, but they play a key role in a part of number theory called class field theory. And this goes back to the famous Jugendtraum of Kronecker in 1880. So I've written here 3 examples of these numbers, and you see whatever they are, these numbers have been known for well over 100 years. Like j of 163 is this very big 18-digit number that presumably I could point at, yeah. What we found was very, very surprising because nobody had noticed it, even in the tables, which had been around for 100 years. We found that each of these numbers, when you split it into prime factors, has very many, very small prime factors, which is extremely unusual, and any difference of 2 of them. So I've given here 2 examples. If you take this 18-digit number, if you split it into primes, a typical 18-digit number would have 3 or 4 very big prime factors. But this number's 5 prime factors, all less than 30, but to high powers, 2 to the 18th and so on. And similarly, if you take the difference, I mean, any example would work, but here I took this number minus this number. It's again an 18-digit number, but again, it factors in a very, very specific way. What was surprising about this is first, as I said, it had never been noticed, although these numbers were super famous and people could have just seen that they had this property. But it's the only case I know, I haven't written that, so I'll keep it. Oops, how do I go back? It's the only case I think I know in all of mathematics where there's a naturally occurring number and you can predict, you can say theoretically, what its prime factors are. Usually if you have a big number, you can take a computer and factorize it, but you have no expectation that these numbers turned out to have some very systematic properties. The second application is actually much more important. This is in the field of elliptic curves. And since that word is certainly not familiar to non-number theorists, I'll say very briefly, this is part of the theory called Diophantine equations, after a 2nd century Greek mathematician, Diophantus of Alexandria. And here's a typical question. I want to emphasize this question because it tells you something about what mathematics, what pure mathematics is like. So this is a problem that Fermat, you've all heard of, posed in 1643, fairly artificial problem. You have to find a right-angled triangle. So we all know Pythagoras' theorem. It means ABC, a squared plus b squared equals c squared, with integer sides and hypotenuse. But you require that the hypotenuse, the biggest side, is a perfect square, and the sum of the 2 shorter sides is also a perfect square. And this is incredible to me. With no machinery, no telescopes, no microscopes, no computers, just with the human mind, Fermat was able to show that there are infinitely many, and that the smallest one was this triple of absolutely gigantic numbers, these 3. And you can check it, this number squared plus this number squared is that number squared, so they do indeed form a right-angled triangle. The big number, this one, is a perfect square, and the sum of the 2 is a perfect square. You can check this, even by hand, in half an hour with the computer in a millisecond. But to find it, not knowing anything, just using this, that to me shows what pure mathematics can be about, that it's possible for the human mind to solve such a problem without any assistance. Anyway, that's a long digression on my favorite field. But as many of you may know, for the new millennium, 7 problems were chosen, for each of which there was a prize of $1 million. 1 has been solved, 6 haven't. And one of them is the Birch and Swinnerton-Dyer conjecture, still unsolved. And it predicts exactly when equations of this form do have infinitely many solutions. So Fermat showed that his particular problem had infinitely many. But for any given problem, it can be very, very difficult. So this conjecture, which is still open, answers that completely. It says exactly when it happens. And our formula, somewhat unexpectedly, showed for a very large class of cases that this conjecture is true, that those cases include Fermat's problem. The third application still of the work with de Grosse and of this very complicated one-page identity with 100-page proof, which was mentioned already, the solution of what was called the Gauss class number problem, which went back to the Disquisitiones, which was published in 1804. So this was a very famous problem. It had been partially solved by previous mathematicians, but there was one crucial step missing, and this turned out to follow from what we had done. So that's the work with de Grosse and 3 applications within number theory. My time is probably running out, but I wanted to say the other 2 fields, which are much more recent for me, much more briefly. So one of them was not meant to be mathematical physics. That was a big surprise. As I said, my field is modular forms, but there was a famous letter written to, just before he died, by Srinivasa Ramanujan, the Indian genius who died in 1920 at the age of 32. And he wrote to his friend G.H. Hardy that he had discovered new functions called Mach theta functions. And a student of mine in his thesis understood how they worked and that they were part of a new theory of modular forms called Mach modular forms, something more general. Then, quite unexpectedly, about 15 years later, it turned out this was joint work with 2 Indian friends and colleagues, Samir Murthy and Atish Dabholkar, who's now my boss because he's the director of the ICTP where I work. We developed a theory that relates these very exotic new things, these Mach modular forms, to a question in, admittedly, very theoretical physics, the string theory of black holes. Physicists argue whether string theory is physics at all or just mathematics, but anyway, it is certainly mathematically feasible. And what we showed is that the physicists love very colorful terminology. This I find rather amusing. And so they have a class of these called immortal black holes. So sometimes 2 black holes come together like 2 galaxies and they merge. But there are some that pass through and are always there. They call them the immortal ones. They have their own nature. And their quantum numbers, these are very complicated quantum numbers, are therefore well-defined integers. And those integers turned out to be exactly given by the coefficients of such a Mach modular form. So this was a beautiful application of a rather new theorem, a new theory of pure number theory in a very, very distant seeming domain of physics. And the last thing, this would be my most recent work. As I mentioned, I started out in topology. In the last 10 years, I got back into topology through work in particular with my friend Stavros Karoufalidis, a Greek-American mathematician. And this is on quantum invariance of knots and 3-dimensional manifolds. Again, of course, I cannot explain what this means. The word quantum suggests that the definition of these invariants comes through people like Witten from ideas of quantum field theory, but there are very specific numbers that you can compute. You have a knot, and you can compute these numbers of these functions. And we studied them for more than 10 years, and they turned out to have, which I think we had not and nobody had expected, very deep arithmetic properties, not just coming from topology, not simple properties, including a new kind of modular form, which I found and called quantum modular forms, and now quite a few people are studying. The theory is still in its infancy. So this had several applications in topology, but it also had several going back to pure number theory. And I mentioned just 2. There are several technical words. One is a construction of units in certain number fields. I can only say that one of the key problems of algebraic number theory is to construct units, and there are no general methods. But this was one quite large class of fields for which we were able to do that. This was with Garofalidis and Frank Caligari. I need only one. Then the other that I mentioned specially, there's a thing which should be a beautiful object in number theory, which as I wrote, it is a beautiful object in number theory, but if you ask 20 number theorists, none of them have heard of it. The people who know it are all topologists, because this thing was found in topology about 15 or 20 years ago. Many topologists know it, but it hasn't yet caught on in number theory. It's just beginning. And this is called the Habiro ring. Habiro is a Japanese mathematician. This is his name. And through the work with Garofalidis, we found experimentally that these new invariants lay in some, or belong to some new object which generalized the Habiro ring. It was clear that that was true, but we couldn't make a definition. And then together with Peter Scholz, a very famous colleague of mine in Bonn, a fields metallist, and Campbell Wheeler, who was our joint PhD student, we have now made this generalization. And so I just end by saying that things on this last page I started 45 years ago, but all of this is rather recent, and the paper on the Habiro ring, originally I hoped I could have told you it was finished yesterday, but it will be finished this month. But I'm finished now. So thank you very much.
Thank you very much for your interesting presentation and being perfectly in time. Are there any questions?
Yes. So did you about the primes appearing values of
about the primes appearing in the decomposition of the singular values? Did you notice it, or did you notice after the Gross-Zagier formula?
I actually felt very stupid, because what I tell all my colleagues is if you do calculations, the first thing you should do is look at the answer, look at the numbers, study the tables, look for patterns. But we didn't. We proved the theorem, and then we noticed that it would imply this factorization. And we told each other, we must have made a mistake. It's impossible. It's much too beautiful. No number in mathematics can be factored. And if it were true, everybody would have noticed it. The first table of these numbers, very big, was published in 1927, more than 50 years earlier. So we told ourselves we must have done something stupid. But then we looked at the numbers, and it's true. So that's a very good question. And I felt stupid that we hadn't noticed it, but it was very nice to discover it theoretically also.
There is another down there.
Yeah?
Well, if we look at the two pictures, Plato point to the sky and Aristotle to the earth. And one is the true world, quote unquote, sky, and the earth is the real world. And if I say what is true cannot be real, and what is real cannot be true. So for a physicist or applied mathematics, if the concept of truth that they are looking at most is a modulated truth, not sort of the truth that Plato has in his mind. Would you sort of entertain that?
Well, that's exactly the difference of philosophy, I think, of the different types of physicists, theoretical and more applied, and mathematicians. To me, it is clear that I'm completely Platonic. The truth of mathematics is there. It has nothing to do with us. The formula that Gross and I found was, of course, there before. We just noticed it. These numbers had that factorization. This truth is absolute. Little accidents like dark matter and so, if our universe had been arranged a bit differently, of course, we wouldn't be here, but it would be something else. But these mathematical truths are absolute. They couldn't be otherwise. And so it's very exciting, if this is your personal feeling, as it is mine, to work on things that you feel you're not inventing something, you're discovering what is there, and discovering something that will never change. No one can take it away, it will never become false. But the bad side is, of course, it may remain irrelevant and unimportant forever, but that's the price you pay.